We will start this session with the topic Differential Scanning Calorimetry, DSC. I am Dr. Jinish. I am from Ramaya University of Applied Sciences. Differential scanning calorimetry is a thermo-analytical technique in which the difference of amount of heat required to increase the temperature of a sample and reference are measured as a function of temperature. Differential scanning calorimetry is a thermal analysis technique. So we will be getting information about the thermal properties of different materials using differential scanning calorimetry. Why the name differential scanning calorimetry for this technique? Differential means an amount of difference between things that are compared. Scanning means temperature is ramped. Calorimetry means the process of measuring the amount of heat released or absorbed during the chemical reaction. Differential, an amount of difference between things that are compared. So in differential scanning calorimetry, we are analyzing the difference in the amount of heat required to increase the temperature. So this difference is differential in the name. Scanning means either we will increase the temperature and measure the heat flow, or we will keep the sample at a particular temperature for a long time and check the heat flow. In these two cases, either we are changing the temperature or scanning the temperature or changing the time or allow the reaction or allow the material to stay at a particular temperature and measure the heat flow on time. That's why the term scanning, from low temperature to high temperature or high temperature to low temperature, or from keeping the sample for a long time at a particular temperature. So either the time is scanned or temperature is scanned. Calorimetry means we are measuring the amount of heat released or absorbed. So calorimetry means measurement of heat produced or absorbed. So two images of differential scanning calorimetry instrument from two different companies, Perkin-Elmer and TA Instruments, where we will use differential calorimetry. Here I am giving you few examples where DSC is widely used in material science. It can be used in many industries: pharmaceutical industry, polymer, nanomaterial, food product. All these industries can use differential scanning calorimetry to study about thermal characteristics of their materials or products. The information these instruments generate is used to understand amorphous and crystalline behavior, polymorphism in a material, eutectic transition, curing and degree of cure, and many other material properties used to design, manufacture, and test products. So using differential scanning calorimetry, we can get many informations, many characteristics of materials such as amorphous and crystalline behavior in a material, whether the material will show polymorphism or not. Is there any eutectic transition in a mixture of sample? If it is related to polymer, whether the polymer is curing or at what temperature the curing starts, how much curing, the degree of cure, all these informations we can gather from differential scanning calorimetry. And these informations will be able to help us to design and manufacture the products required for different applications. Knowledge of materials' heat capacity and heat content change, we call it as enthalpy, is used to estimate how efficiently processing or distilling materials can be done. DSC helps to measure heat capacity and heat content change of a material. So by measuring the heat capacity, by measuring the heat content change of a material, DSC can be used to design the processing methods or distillation methods or separation methods in in chemical industry or in any other materials related industries. DSC is the most common thermal analysis technique and is found in many analytical, process control, quality assurance and R&D laboratories. We will start the working principle and instrumentation of differential scanning calorimetry. DSC is a thermal analysis technique that looks at how a material's heat capacity is changed by temperature. So when we change the temperature, we are checking whether the material's heat capacity is being affected or not. For example, a sample of known mass is heated or cooled and the changes in the heat capacity are tracked as the changes in heat flow. So we will take a known amount of sample in DSC and either we will increase the temperature or decrease the temperature, and we will see during these temperature increase or temperature decrease, is there any change in the heat capacity. If there is any change in the heat capacity, then there will be definitely a heat flow will be happening. So with the help of the heat flow change, we will be able to calculate, or we will be able to tell what is the thermal characteristics of that material. This allows the detection of transitions such as melts, glass transition, phase changes and curing. So by analyzing the heat flow based on the temperature changes, we will be able to measure the melting temperature, glass transition temperature, any other phase transition temperature, any phase transition occurring or not, and if it is an elastomer, is there any curing happening during the temperature increase. All these informations we will be able to gather through DSC. It is a technique in which the energy necessary to establish a zero temperature difference between the sample and reference material is measured as a function of temperature. How this instrument works: we will be having a known sample, which is our testing sample or testing specimen. Same time, we will be taking a reference sample also. And we will be heating both these things, reference sample as well as our working sample or testing sample. We will try to heat it and try to maintain a zero temperature difference. In order to maintain the zero temperature difference, definitely we have to give more or less temperature, less heat to keep to the sample that we are testing to maintain the uniform temperature or the same temperature, or there is no temperature difference. To maintain a zero temperature difference, we have to alter the amount of heat that we have to supply to the testing sample compared to the energy or the heat that we supply or heat we got to or from the reference sample. Sample and reference materials are heated by separate heaters in such a way that their temperatures are kept equal while these temperatures are increased or decreased linearly. So as I said, we have to heat the sample and the reference material in such a way that their temperature should be same, or we can call that there should not be any temperature difference. And normally we will be heating both these sample as well as the reference material using different heaters. For example, if a sample absorbs some amount of heat during a phase transition, then the reaction is said to be endothermic. In endothermic reaction, more energy needed to maintain zero temperature difference between the sample and reference: melting, boiling, sublimation, and vaporization. For example, we have a sample and we have a reference material. We are giving heat to both sample and reference material in such a way that both will have the same temperature. Imagine we are increasing the temperature, maintaining the equal temperature. For example, 30 degrees Celsius, both should be 30 degrees Celsius. I am increasing the temperature to 40 degrees Celsius, so both the samples should be 40 degrees Celsius. Like that, 50 degrees Celsius, 60 degrees Celsius, or you can cool also. Now imagine that this at a particular temperature, the sample is undergoing melting. Melting means a phase transition. So for the phase transition, heat will be utilized. So if heat is utilized for the phase transition, then what will happen? The amount of heat that we supply to the sample will be used for the phase transition, not for the increase in the temperature. But at the same time, reference material is not undergoing any phase transition, so the heat that we supplied to the reference sample will be only used to increase the temperature. So what happens? There may be a chance that the reference sample will show higher temperature compared to the sample. So but we have to maintain the same temperature. So what we should do? We have to supply extra heat to the sample to counteract the heat which will be utilized for the phase transition. So once you supply more amount of heat, that heat will be taken by the sample for the phase transition, and the remaining heat for the increase in the temperature of the sample to maintain equal temperature with that of the reference sample. Now you see that this sample, now it took more amount of heat, so there will be a heat change we will be able to observe in the sample when it reaches its melting point. So this reaction is an endothermic reaction. So during an endothermic reaction, inside the sample, there will be a drastic heat flow change will be observed, and that will indicate that the material undergoes melting. Similar to melting, boiling, sublimation, vaporization, all these points are phase transition steps. Everywhere a heat change will occur in endothermic way. If sample released some amount of heat during phase transition, then the reaction is said to be exothermic. So exothermic means the sample undergoing a reaction where heat is released. Those kind of reactions are known as exothermic reaction. In the case of exothermic reaction, we know that heat is liberated, so the sample will be having more heat or more temperature compared to the reference if it allows normally, but we have to maintain the temperature same. So how it will be done? We know that we have to supply less amount of heat to the sample to maintain the same temperature. So here also there is a heat flow change that will be measured. Here the heat flow change will be with respect to the exothermic reaction. So when these exothermic reactions will happen during crystallization, degradation, and polymerization, where heat will be released by the sample. So we don't have to supply this energy that we were giving before to maintain a zero temperature difference between the sample. Instrumentation. So we know that we need the sample and the reference. In sample pan means, for example, you have a pan. For example, for polymer sample, we normally take an aluminum pan. So inside the aluminum pan, we have to keep a known amount of the sample and we have to close it by pressing. In another furnace, only the aluminum pan, no material inside. And this pan itself, we will call it as the reference pan. That also should be closed. Both should be kept in two different furnaces, and both temperature of the sample, both the sample as well as the reference pan should be measured, and with the help of thermocouple, the heat to be given to the sample pan or the sample pan or can be maintained or can be programmed with the help of computer along with the help of a thermocouple. There are two pans. One is the sample pan where polymer is added, while the other reference pan is left empty. It will not have the sample. Each pan sits on top of the heaters which are controlled by the computer. The computer turns on heaters and lets them heat the two pans at a specific rate. So rate can be 2 degrees centigrade per minute, to 5 degrees centigrade per minute, 10 degrees centigrade per minute, based on the experiment that you perform. The computer makes absolutely sure that the heating rate stays exactly the same throughout the experiment. So exact same heating rate. Why heaters don't heat at the same rate? The sample pan is that the two pans are, the simple reason is that the two pans are different. One has polymer in it or the sample in it and the other one doesn't. If the sample means, the polymer sample means there is extra material in the sample pan. Having extra material means that it will take more heat to keep the temperature of the sample pan increasing at the same rate as the reference pan. So the heater underneath the sample pan has to work harder than the heater underneath the reference pan. It has to put out more heat. That's why to maintain a temperature, zero temperature difference between the sample pan and the reference pan, we require two different heater systems. Otherwise, same heater system if you supply, definitely the sample pan will not get the same temperature as that of the reference pan, because some amount of the heat will be utilized to heat the sample present in this sample pan. That's why we require two different heaters, not in the same heater. The result of a DSC experiment is a curve of heat flux versus the temperature or versus time. So in x-axis, in y-axis, it will be heat flow. We can see that sometimes heat flow is on opposite direction based on whether the reaction is endothermic or exothermic. X-axis, generally it will be temperature. If you are scanning the temperature, if you are scanning the temperature from low temperature to high temperature or high temperature to low temperature. Or we can maintain the sample at a particular temperature and check the heat flow with respect to time. Then it will be time scanning experiment. There are two different conventions. Exothermic reactions in the sample shown with a positive or negative peak depending on the kind of technology used in the experiment. This curve can be used to calculate enthalpies of transitions, which is done by integrating the peak corresponding to the given transition. For example, this peak is for melting. So if you take the area under that peak for the melting, then we will get information about enthalpy of melting. Similarly, you are getting a peak here for crystallization, recrystallization. If you take the area under the curve, then you will get enthalpy of crystallization. So the enthalpy of transition can be calculated using the equation delta H equal to K into A. K is calorimetric constant and A is the area under the peak. So if you got the area under the peak, then by multiplying with the calorimetric constant, we will be able to get enthalpy of transition such as enthalpy of crystallization, enthalpy of melting, etc. First, how we will determine the heat capacity of the sample. DSC plot can be used to determine the heat capacity. Suppose a polymer is being heated. When we start heating two pans, the computer will plot the difference in heat output of the two heaters against the temperature, that is plot of heat absorbed by the polymer against the temperature. The plot will look like this at first. So initial part of the DSC curve, you will get a straight line. Reason: during that time, we are supplying heat to both the reference pan and the sample through different heaters, and we have to maintain the same temperature during that temperature increase. But we know that the sample pan contains polymer, so we have to give more heat to the heater, through the heater to the sample pan. How much heat will give you information about the heat capacity. So heat capacity can be calculated using the equation Q by T. So here, if you see the equation Q by T, by measuring the time, and by measuring how much heat we have given to the sample, all these informations leads to calculation of heat capacity. Now, how we will determine glass transition of a temperature. Some materials such as polymers, once you decrease the temperature, below a particular temperature, the sample will become become glassy. Or if you increase the temperature above that particular temperature, the polymer will become glassy to rubbery. That transition temperature is known as glass transition temperature. So glass transition temperature is one of the most important properties of any polymer and is the temperature region where the polymer transitions from a hard glassy material to a softy rubbery material. For example, for a silicone rubber, some of the silicone rubber grades have a glass transition temperature of minus 120 degrees Celsius. Means below minus 120 degrees Celsius, this silicone elastomer will behave hard and glassy. Above minus 120 degrees Celsius, silicone elastomer will act as rubbery. So minus 120 degrees Celsius is the glass transition temperature of the elastomer. In the case of if it is an elastomer, if that elastomer is in glassy state, then it will be brittle and we cannot use that elastomer for any application below that temperature. Next is determination of crystallization temperature. Crystallization temperature is represented using the letter Tc. After glass transition, the polymers have lots of mobility. So once the sample is having a temperature higher than that of glass transition temperature, the polymer have lots of mobility. Polymer chains will have lots of mobility. When they reach the right temperature, they will give off enough energy to move into very ordered arrangement, which is called crystals, and the temperature is known as crystallization temperature, and the area under the peak can be used to calculate the enthalpy of crystallization. So after a particular temperature or below a particular temperature, then what happens? The polymer or the molecules will be arranged in a particular ordered arrangement, which is called crystals, and the temperature is known as crystallization temperature, and the area under the peak can be used to calculate enthalpy of crystallization. Most of the polymers, this crystallization temperature will be visible when we cool the material from higher temperature to the low temperature and measuring the heat flow using differential scanning calorimetry. How we will determine the melting temperature? To measure melting temperature, we have to heat the sample from low temperature to high temperature in differential scanning calorimetry. If the sample passed its crystallization temperature, eventually it will reach another transition called melting. So at this, when it melts, we know that is an endothermic reaction. Some amount of heat we require extra to give to the sample to maintain a zero temperature difference. So we will get an endothermic peak in DSC curve, and area under that curve we call it as enthalpy of melting, and the temperature at this peak, this temperature is, we will call it as melting temperature or Tm of that sample. Now we know that we may get the specific heat capacity from the initial part of the graph. Then we may get the glass transition temperature, crystallization temperature and melting temperature from this plot of a polymer. For example, here you see it's a polyethylene terephthalate polymer generally used for making water bottles, especially one-time usable water bottle. You see its DSC curve. So we can see there is a glass transition temperature in the range of somewhere around 60 degree to 70 degree. There is a recrystallization temperature in the range of somewhere around 130 degrees Celsius and a melting peak somewhere around 260 degrees Celsius for polyethylene terephthalate. Advantages of DSC: we can rapidly measure the thermal characteristics. Small sample masses, in milligram level only you require the sample. Instrument can be used at very high temperature, but we have to make sure that at that temperature the sample that we are going to test is not degrading. That is very, very important. Instruments are highly sensitive. Characteristics, transition or reaction temperature can be determined. And the stability of the material also can be calculated or measured using differential scanning calorimetry. Limitations of DSC. DSC is generally used only for the thermal screening of isolated intermediates and products. Uncertainty of heats of fusion and transition temperature. There will be uncertainty in heats of fusion and transition temperature. Does not detect gas generation if any reaction is happening. Conventional differential scanning calorimetry will not check is there any gas evolving, if there is a gas involving when we heat or cool. DC is generally unsuitable for two-phase mixtures. So if you have a mixture with two phases, DSC is not a suitable method to study the thermal characteristics. So we will conclude this conclude the differential scanning calorimetry. DSC is a thermo-analytical technique in which the difference in the amount of heat required to increase the temperature of a sample and reference are measured as function of temperature. In polymers, DSC is useful in determining the composition, heat capacity, melting temperature, glass transition temperature, crystallinity, etc. So these are some DSC samples and their sampling machines, so DSC instrument and their sampling machine. Next thermal analytical technique is thermogravimetric analysis, also known as TGA. So one TGA instrument. So TGA, thermogravimetric analysis, is a branch of thermal analysis examining the mass changes of a sample as a function of temperature in the scanning mode or as a function of time in the isothermal mode. So thermogravimetric analysis, in that process, we will be examining the mass change happening for a sample if we are keeping that sample in an atmosphere, whether either we are increasing the temperature and seeing the mass change, or we are keeping the sample at a particular temperature and seeing the mass change with respect to time. In both the way, we will be able to perform thermogravimetric analysis. If you are scanning temperature or if you are scanning time. If you are scanning time and keeping the temperature, then we will call it as isothermal mode based TGA, or we will, or in the other ways, if you are changing the temperature and finding the mass change, those kind of experiment, where is the temperature scanning mode experiment. Thermal gravimetric analysis or thermogravimetric analysis is a method of thermal analysis in which changes in the physical and chemical properties of materials are measured as a function of increasing temperature with a constant heating rate, or as a function of time with a constant temperature and or constant mass loss. So in thermogravimetric analysis, we have to give a known mass of sample, very low amount of sample, and we have to heat if we are doing temperature scanning, and heating rate should be maintained uniformly. And with each temperature, we have to see how much heat is how much mass is reduced. So that mass reduction or the change in the mass should be plotted against temperature if you are scanning against temperature. Or if you are scanning against time, we have to plot a graph where mass change against time to be plotted, and from that graph we should be able to interpret the thermal stability and the other thermal characteristics of that material using the results that we obtained after performing the experiment. Changes in the mass of a sample due to various thermal events for desorption, absorption, sublimation, vaporization, oxidation, reduction, and decomposition. Now, all these reactions, all these changes will lead to a mass change. Sometimes the mass will be increasing, and most of the time mass will be decreasing. And this can be studied when a sample is subjected to a program of change of temperature. So by changing the temperature, we will be able to see how the mass is reducing or increasing based on the reaction happening inside that material in that temperature change. Therefore, it is used in the analysis of volatile products. So it is widely used in volatile products, gaseous product analysis, reactions in thermoplastic thermosets, elastomers, composites, film, fibers, coatings, paints, everywhere we can use thermogravimetric analysis. Now a block diagram of a thermobalance, which is an essential part of thermogravimetric analysis. So here there is a recording balance where we have to keep the sample in a holder. The holder is generally made up of using platinum or ceramic, where both these material can withstand very high temperature. If you want to withstand very high temperature, we have to use ceramics. For example, for polymer, we have to keep the temperature maximum 700 degrees Celsius. For that case, platinum is fine. But if you want to study the thermal characteristic at 1000 degrees Celsius or 1200 degrees Celsius, then instead of platinum, we have to use a ceramic holder to keep the sample. Then that sample holder we will be keeping in a furnace, and that furnace temperature we can measure using thermocouple and can be maintained with the help of a computer and a heating system. So here is a typical plot of a thermogravimetric analysis with the temperature. So we can see the material initially at lower temperature was having higher mass. When we are increasing the temperature, the mass is decreasing, and the maximum amount of heat mass decreased somewhere around this temperature. So here in this graph, if you carefully see, there are two temperature for the reaction in the graph. If you mention, for example, this temperature we write it as Ti, and this temperature we write it as Tf. Ti is the starting of decomposition temperature. So we can see that mass started decreasing at this temperature, and this temperature mass decrease happened. Now there is not much change in the mass. So two temperature we got, we write it as Tf and Ti. So Ti is the starting of the decomposition temperature, and Tf is the final temperature, representing the lower temperature at which the onset of the mass change is seen and the lowest temperature at which the process has been completed, respectively. There are different TGA curves or portion of TGA curves. If you see this curve, we can see that a small increase in mass happened. Here, a small decrease in mass happened, then there is no change in the mass change. Here, a decrease in mass change one time happened at a particular temperature, then there is no change in the mass. Here it is a stepwise mass change is happening. Here also stepwise mass change at a faster rate. Here little bit heat is mass is increasing, and then it is going straight. Here also heat is when you increase the temperature, mass is increasing a little bit, then it is decreasing. So several trends we can see in TGA curves or in a portion of TGA curves based on the material that we took and the reactions the material undergoes during the temperature increase or decrease, mainly temperature during the temperature increase. So when the mass will increase, the weight will increase, and when the mass will decrease, the weight will decrease. So for absorption, and if during the heating, if adsorption or absorption occurs, definitely weight will be gained, like in this case. Desorption, drying, definitely the molecule will be escaped from the material. Some molecules will be escaped from the material. So definitely weight loss will occur. Dehydration, desolvation, weight loss will occur. Sublimation, weight loss will occur. Vaporization will occur. Solid state reactions, weight loss mainly will occur. Solid gas reaction, both can occur. Some reactions will lead to weight gain, and some reactions will lead to weight less. Magnetic transition, same thing. Some can lead to weight gain and some can lead to weight loss. So these are the processes that can happen to the sample when we allow the sample to undergo TGA analysis or TGA experiment. So this is an example of a calcium-based compound, which is Vevalite. So here we can see in this TGA curve, one set of mass change, second set of mass change, then third set of mass change. So generally, there are 3 stages of degradation happening for this sample when we increase the temperature from room temperature to 900 degrees Celsius. We can see that the first degradation, during the first degradation, 12.28% of the sample is being lost. where it going lost, because after the degradation, some of the degraded products, around 12.28% of the degraded products are gaseous molecules. Definitely they will go out, so the sample weight will be reduced. Then around 400 degrees Celsius, you can see again a temperature, a mass change happened, drastic mass change happened, and we can see that from here to here, almost 18.06% of the mass is being taken by the elimination of gaseous molecule after the second stage degradation. In the third stage degradation, we can see that around 29.22% of the remaining sample is being lost due to the degradation and formation of gaseous molecules or gaseous compounds. The remaining around 39.75% of the sample is keeping constant. That means further degradation is not happening up to 100 degrees Celsius. We will call the remaining, that 39.25, as residue or ash content. Ash content or residue. They will be mainly the salts which won't be degrading at higher temperature. So that will be the ash content. So from this graph, we will get information about in which temperature the material started degrading and how many stages of degradation of mass is happening. And also we will be able to see the ash or residue content from this graph. Now, if somebody asks a question, this transition really happening not in a single temperature, using actually degradation happens from starting from here, end from here, starting from here, ends up to here. So we can see that the temperature, there is not a single temperature where the degradation is happening. It actually a series. So at what temperature maximum degradation is happening in each stage, if you want to know that, then we have to take a derivative graph of this thermogram. This graph is known as thermogram. So if you take a derivative thermogram graph, then like this. For this same compound, this red line is the thermogram, and if you take the derivative of that thermogram, then we will get derivative thermogram. Derivative thermogram, if you see, they have distinct peak. So from that peak, if you draw a line to the x-axis, it will meet the x-axis at a particular temperature. That is the temperature where the maximum degradation happening in the first stage. Similarly, I can calculate the second maximum degradation temperature for the second degradation, maximum temperature of degradation for the second degradation. Here also I can calculate the maximum degradation temperature in the third stage of degradation. So all these informations I will be getting if I take a derivative thermogram. So derivative thermogram, you see it is weight change because we are taking the derivative. So if you take a thermogram, and if you take its derivative of thermogram, we will be getting information such as maximum degradation temperature, when onset of degradation, at what temperature degradation started, at what temperature degradation finished, what is the residue of or the ash content present in the sample after the degradation, complete degradation. Applications of thermogravimetric analysis. Thermal stability of the related materials can be compared at elevated temperatures under the required atmosphere. So we will be able to compare the thermal stability of different compounds, and we will be able to identify which compound is having the highest thermal stability compared to others. Materials characterization. TGA curves can be used to fingerprint materials for identification of quality control. For example, you are getting two materials and you wanted to confirm that whether these two materials, in these two materials, which is the right material which can be used for the applications. So for identification of the quality control, we will be able to use thermogravimetric analysis. We will be able to study about compositional analysis. Compositional analysis means if you are getting a composite or a mixture, and if you want to know that how many components are there or in which ratio the components are mixed to make this mixture, all these things actually you can measure using thermogravimetric analysis along with some other techniques, not only with the TGA, with other technique. For example, in a rubber composite, how much carbon black is present, how much filler is present, how much oil is present, how much moisture is present. All these informations we will be able to get from thermogravimetric analysis. Also, we will be able to perform kinetic studies where you wanted to find the speed of the reaction, rate constant of the reaction. In those cases also, we will be able to use thermogravimetric analysis. Also, thermogravimetric analysis provides information about the corrosion happening inside the sample, because corrosions are oxidation reactions generally happening, and most of the time the reaction happens or reaction produces some reactive gases or vapors which will change the remaining compound's mass. So that technique can be used for studying the corrosion studies.